have Frederic Nallet here, and he's going to talk about stabilizing water in water emulsion with swollen lamellar phases. Thank you, Frederic.
Okay, thank you. So, good morning to everyone. It's my pleasure also to be here, and I've been invited specifically by Cristiano, and perhaps there will be some strange things here today, because this is about experiments, in fact. Yesterday, when we, some of us went to Sirius, it appeared that most of us are not experimentalists. So I'm feeling a bit, strange in a sense. I hope what I will present in front of you can nevertheless have some interest. So as it is said here, we are trying in Bordeaux to stabilize water in water emulsions using swollen lamellar phases. And water in water emulsions are systems that are very commonly obtained by liquid-liquid phase separation, which is an equilibrium mechanism, so nothing living here, just standard equilibrium thermodynamics. When typically a polymer A is dissolved in water and it is mixed with a polymer B, also dissolved in water, and when you mix the two mixtures, shake that, in some cases you have a phase separation with a droplet rich in polymer A, for instance. Perhaps, yes, this marked in green on the screen. That phase separate from the matrix, which is in fact a solution rich in polymer B, unmarked. So that's why it's it appears in black on this picture. And as a phase separated system, it is in principle unstable, kinetically speaking, and it should evolve in time with these small droplets coalescing with the bigger ones, and in the end you should reach a completely phase separated state with, let's say, the lower part of the cell that will be filled, say, by the green tagged solution, with floating above it the black tagged as suspension. And while this is quite a common phenomenon, and liquid-liquid phase separation occurs, of course, typically when mixing oil and water, and these are ordinary emulsions like milk, for instance, or mayonnaise, if you like, and it is usually of some practical interest to stabilize those emulsions, because as phase separated system, there is a surface tension at the interface, which is the droplet and the continuous phase. And that surface tension is typically large in usual oil-in-water emulsion, but it turns out to be extremely small in the case of water-in-water emulsion, because the inside phase and the outside phase are basically essentially water. So with a small interfacial tension, it's still a tension. You see the droplets are round. Perhaps, it is a 2D projection. So the droplets are in principle a spherical object. But that small surface tension is enough to make those droplets round. And also, because there is a surface tension, this will be driving the coalescence phenomenon. And to, let's say, to delay that process, stabilizing agents are usually added to the mixture in order to say to populate the interface of the droplets, and this is what we have been doing in our lab, using particular kind of stabilizing agent, which are the swollen lamellar phases. And on that picture, the part of the species that is associated to the swollen lamellar phases is tagged in red, and you see that, well, basically it works. The interface between the inner part, which here is tagged in green, and the outer part, which here is tagged in black, not tagged, untagged in fact, so the lamellar phase stays at the interface. Well, perhaps you realize that the thickness of this interface appears to be quite visible at the scale of the picture. By the way, what is the scale of the picture? I've forgotten to include it. It's the typical diameter of the large object is perhaps 40 micrometers here. So the interface between the polymer B containing phase with the polymer A containing phase appears to be quite large. Well, this is also quite a classical idea, that the thickness of an interface between phase separated media is related to the interfacial tension. So the lower the interfacial tension, the wider the interface. So in this talk, I will try to describe the well, have some ideas related to the liquid-liquid phase separation. So the particular case of stabilizing agents as swollen lamellar phases, and the fact that apparently experimentally it works, even if at the let's say not really the theoretical level, but at the level of thermodynamic descriptions of the problem, we are far from understanding things. So I will first try to well, to review in very simple terms, I hope, and very familiar ones, because this is basically almost textbook thermodynamics, the properties of the liquid-liquid phase separation. So not the motility-induced phase separation that we have heard about before, but the standard liquid-liquid phase separation in first two-component systems, and in a slightly more complicated case of three-component systems. Because, well, the water and water emulsion are basically three-component systems. So I will then talk about the let's say, strange or unusual properties of lamellar phases that could be either in the swelling regime or perhaps in their bond regime, and what is the relevance of that peculiarity for swollen lamellar phase, especially in terms of curiosity, which is then binding transition, in elaborating the main objective, which is stabilizing water in water emulsions. So I first start with a very hopefully simple consideration. There is a lot of equations written in very small characters perhaps, but this is actually very standard. Again, so we, in the case of a two-component incompressible system, typically the thermodynamics is described by the Gibbs free energy, which itself depends on the on the free energy density that is typically in standard description described in terms of mixing entropy here and interactions between the solute and the solvent. So this chi parameter here describes the interaction, and the log terms describe the mixing entropy. Well, this is terribly classical, of course. You can derive from that the osmotic pressure associated to that two-component mixture, and you recover the famous Van 't Hoff law, of course, that the osmotic pressure is proportional to the solute concentration, at least in the limit of small concentration. Since we are interested in water emulsions where the components are polymers, we have to extend that. Well, it has been done long ago, of course, to take into account the property of macromolecular solutes being introduced into the system, and this is in fact the extension of the standard model by Flory and Huggins long ago. And the main new ingredient is the degree of polymerization in the system, which is the number of basic chemical units that are linked together to make a long chain. And in that particular case, this has a huge, in fact, impact on the mixing entropy, and some kind of impact also on the interaction between the objects. So the normalization that has been chosen here is perhaps a bit misleading, because you see the n factor in front of the interactions between polymer and solvent, and mixing entropy apparently unaffected, because it is expressed in terms of the concentration of the solute species, which is the macromolecular species here. But when you do the explicit computation of the osmotic pressure, in the case of dilute macromolecular solution, what you obtain is in fact the experimental properties that long ago was the first hint of macromolecular systems being macromolecular, made with a large number of identical components linked together, is that in terms of the monomer or the mass concentration of the dissolved species, the osmotic pressure is enormously reduced by that factor. And the effect of interaction is magnified by the degree of polymerization, meaning that those mixtures, one polymer and solvent, are quite, let's say, susceptible to thermodynamic strangeness. And, well, strangeness, or not perhaps really strange. We are interested, in fact, in liquid-liquid phase separation, and it occurs in both the simple model and in the case of the macromolecular model, if the interaction parameter is large enough. But large enough doesn't mean the same thing in standard solution and in macromolecular solution, because precisely there is that amplifying effect of the degree of polymerization. And I will try to present here the classical phase diagram that results from that Flory-Huggins model in reduced coordinate. So the scale is a bit too large. But typically for interactions parameter that are smaller than the value associated to that blue point, called the critical point, there is no phase separation. The polymer and the solvent are mixing in whatever proportion. And above that point, there is a phase separation that is apparent here in the phase diagram by those red lines, horizontal red lines, that describes the tie lines between a concentrated polymer solution with a high concentration here that phase separates with an almost pure solvent. In fact, if you zoom in that region, it appears that there is still some polymer dissolved in the dilute phase. When you go to the case of three-component systems, well, the story is the same, a bit more complicated with wilder equations, but with still the same ideas, mixing entropies for the two polymer species and interaction terms. But since there are three types of possible interactions, solvent, polymer, solvent, polymer A, solvent, polymer B, and polymer A, polymer B, there are three interaction parameters here. Well, the phase diagram that results is a bit more complicated, of course. And I have to say that this, in fact, is only applicable to the case of a non-ionic polymer. So the case where the polymer, in this case, would be polyelectrolytes are bearing charges that would change the way the thermodynamics should be described, and so the case of charged polymer is to be described in terms of associative liquid-liquid phase separation. I am here only interested in segregative liquid-liquid phase separation. So the phase diagram requires the usual rules of chemical potentials being equals in the two phase that equilibrates, but chemical potential for each species. So there are in fact three equilibrium condition, chemical potential equality conditions, of course, with the standard constraint associated to volume conservation and mass conservation, of course. And that leads to, and here is an experimental phase diagram, a representation where the upper part is the phase separated regime and the lower part is the homogeneous regime, and the tie lines here are inclined. So the red lines are connecting a phase separated polymer mixture that is enhanced in the dextran polymer here in this case, with a phase that is enhanced in the PEG polyethylene glycol concentration here. And differing from the standard case, the tie lines are not parallel to each other, and they may change orientation. At some point, presumably here, there is a critical point where the tie lines have zero length. Of course, thermodynamic is something related to order and progress, as well known in Brazil, for sure. And the problem to be solved from a theoretical point of view is looks like an optimization problem where you have to minimize the sum of the squares of the osmotic pressure or chemical potential for species A and species B. Which is quite complex practically, but in case there is a stability criterion that generalizes the osmotic compressibility criterion for two component systems, where when the Hessian determinant of the free energy matrix is 0. There are the possibility for fluctuations to diverge. So the system is unstable and certainly should phase separate when the spinodal line is crossed. So it's possible to extract numerically the spinodal line from the generalized Fourier-Gins model, of course. But it's, at least for me, much more difficult to build the phase diagram. So so this is the spinodal line, and there is somewhere in green the binodal lines, and building also the tie lines is quite difficult, but it will be important in order to know the surface tension in the systems, and to relate that surface tension to the width of the interface, and therefore to choose the right stabilizing agent for stabilizing the water in water emulsions. So I move now to the case of lamellar phases. And lamellar phases are, well, stacked objects, stacked structure, the way the sheet of papers here are stacked in this notebook, and they can be swollen by increasing the amount of solvent that separates the sheets. They have some interesting thermodynamic properties, because if you try again to describe the thermodynamic properties of a two-component lamellar phase, so it is bilayer and solvent, let's say the mixing entropy part of the free energy is quite different, because the objects to be considered are, well, extended in 2 dimensions, and maybe fluctuating owing to thermal energy. And quite long ago, Elfrich described the contribution to the free energy related to those undulations, and it turns out that the expression is inversely proportional to the bending modulus of this lamellar phase. Well, the geometry can be simple geometry can be considered, and the concentration in active species, the tensioactive surfactant molecule, amphiphilic molecule, is related to the L, which is the stacking periodicity in the lamellar phase, and to a parameter which is the extension, the size occupied at the interface by one single molecule. Well, basically the interactions can also be described. So, the general principle of balancing entropy of mixing, or a kind of entropic contribution to the free energy with the enthalpic contribution, and at the virial level, this is again proportional to considering some interaction dimensionless parameter to the solute concentration squared for describing interaction of the one layer with another layer. And this model, well, leads to a complicated, perhaps, expression for the free energy with a standard virial term and then, let's say, a non-standard mixing entropy term. And because of that, the phase diagram is quite interesting. For instance, it predicts the existence of a swelling limit in the system. So again, the shape of the figure is a bit too large. Okay, so the osmotic pressure can be predicted from the free energy, and it appears to be in some cases negative, which doesn't make sense, of course, physically speaking. Meaning that there is a specific point here beyond which or below which in surfactant concentration, if you add water to the system to swell the lamellar phase more than described at that precise concentration, the excess water will phase separate. So this is again a kind of liquid-liquid phase separation, liquid crystal, liquid phase separation that we have here. With the so the prediction by Milner and Roux from 30 years ago, something like that there is a swelling limit in the phase diagram if you consider the stacking period L, the reciprocal of the stacking period L, as a function of the concentration. Well, the lamellar phase swells, and then the swelling stops, and it becomes bond, as it is said, having a perhaps large but finite and no longer varying value. So this can be translated into a phase diagram that perhaps looks like visually more or less like the one associated to the simple polymer case, but the interaction parameters vertically and the concentration, again, this is a bit not visible on that axis. So for large concentration, you have a homogeneous lamellar phase, swollen lamellar phase, and if you increase the amount of water, at some point you will reach the binodal green lines. And if you add more water, so you try to explore the tie line, the horizontal tie line, the solvent that you add will get, and in this case, to exactly zero concentration of surfactant molecules. So that line here is pure solvent. But that phenomenon doesn't exist in the case where the interaction parameter is below 0, which leads to the unbinding transition, meaning that if you now plot the, let's say, the difference in concentration between the bond lamellar phase that is obtained with the 0, which is the pure solvent concentration, as a function, so here is the difference in concentration as a function of the interaction parameter. You have a kind of critical phenomenon with in log representation a decrease to 0 that depends on the power law on the interaction parameters, with a critical exponent that is here beta equal to 1. And so we that unbinding transition, or that swelling property associated to lamellar phases, is giving some clue to stabilizing water in water emulsions, because as the optimum concentration, the more the optimal concentration that the lamellar phase can have can be made arbitrarily small if you can control the interaction parameters, it means that you can adjust the characteristic size of a lamellar phase, perhaps to fit the width of the interface between the polymer A-rich dispersed phase with the polymer B-rich continuous phase. And you might think of using the dilute lamellar phase as a stabilizing agent, large-scale stabilizing agent. Unfortunately, the problem is a bit more complicated because, in fact, we are considering 3-component systems. There is an even 4-component system in the end. And in particular, the experimental situation associated to the swelling of lamellar phases in the presence of a solvent that contains polymer is quite complicated. So along the horizontal line, you would be swelling a lamellar phase with pure water, but along those lines, you will be swelling the lamellar phase with a solvent that contains some amount of polymer. And in the middle of that region, there are lamellar phase that phase separate with another lamellar phase that has been established experimentally quite long ago, with even the critical point, or at least a special point, related to that lamellar phase separated with another lamellar phase. But still you have the swelling behavior that can be explored here until you get that limit which corresponds to the bond regime of the lamellar phase. And for instance, at that point of the binodal line, you would have a lamellar phase that is swollen by a large amount of polymer in equilibrium with a solvent that contains some polymer in it. So that makes the thermodynamic description of the problem quite difficult, because we would like to mix together the Flory-Huggins model for polymer solvent mixture and the Milnor-Roux problem for the lamellar phase in a consistent way. Well, since we can from Flory-Huggins compute, again, don't pay attention to the shape of the equations, the polymer chemical potential and the water chemical potential. We will also think that in the problem where the polymer dot solvent is used to swell the lamellar phase, the polymer will be constrained in space by the presence of the bilayers themselves. So that's why we can think of renormalizing the concentration by that swelling factor. That will obviously depends on the periodicity of the stacking in the lamellar system, and therefore introduce in the expressions for the chemical potentials a dependence on surfactant concentration. So this is perhaps not really dangerous or harmful in the case of the polymer, where we have just applied here in that complicated formula the renormalization factor for the polymer concentration, but that cannot be presumably done as easily in the case of the solvent, because the very existence of the bond regime of the lamellar phase when it is swollen by the polymer containing solvent is something that we think is important, and it is also observed experimentally. So we would like to change the chemical potential for water not coming from the Flory-Huggins source, but from the Milnor-Roux source, and that would be that complicated experiment. And again, this is because we want to keep the idea of unbinding transition, let's say, in polymer doped lamellar phase. Well, so that would be nice, but we are constrained by the fact that the chemical potentials are interlinked together by the well-known Maxwell equations or relations in thermodynamics, and we have to find a way which is not yet found of introducing perhaps concentration dependence of the parameters that relates the area occupied by the surfactant molecule at the interface in the laminar phase to the polymer concentration in the solvent. Perhaps also introduce a polymer dependency on the interaction parameters related to the bilayer interactions for having those three relations consistent in all respects. So, well, I'm now coming back to the experimental part of this. So even if let's say the modeling problem is not solved yet, experimentally it somehow works. So this electron microscopy picture here tentatively shows a droplet that is filled by let's say the polymer B-rich solvent, separated from the matrix, which is the solvent with the polymer rich in A, with in between a kind of let's say skin that could be, if I find the pointer here, interpreted perhaps the stacking of perhaps three layers of a laminar phase. So this system has indeed been prepared by preparing an ordinary water in water emulsion and adding to it the surfactant species able to make a laminar phase. So it also works quite well at a larger scale with on those images where the untagged polymer is inside, the tagged polymer is outside, the tagged surfactant is at the interface. So we have been characterizing a lot the dilution properties of the lamellar phase, so evidencing for both polymer the existence of a bond regime with so this is the periodicity of the stacking that stops when the dilution is quite high, so the amount of solvent is large for the green polymer, green tagged polymer and the untagged polymer. So if you prepare the emulsion by mixing everything, polymer A, polymer B, water, and of course the laminar phase, and if you control the amount of surfactant molecules, you are able to produce more or less stabilized droplets that are becoming smaller at higher surfactant content, and for both kind of system when the green tagged polymer is outside and the not untagged is inside. And this can be interpreted in terms of a kind of optimal coating model that is inspired by the ideas that are describing, in fact, the Pickering emulsions, with the very ideas that the interface between the droplets and the continuous phase has to be optimally, let's say, coated by the stabilizing agents. So in the case of Pickering emulsion, the stabilizing agent is a solid colloidal particle. In our case, the stabilizing agent is a dilute lamellar phase, hopefully in its bond regime. So in a very simple argument, we are counting the layers n for a given stacking period that should match the thickness of the interface, and then you are counting the area to be coated, and you are counting the number of droplets per unit volume, and in the end you reach a very simple relationship between the diameter of the optimally coated droplets to the surfactant concentration, with parameters that can be measured by X-ray scattering, for instance, estimated from literature, and with that unknown quantity, in principle related to the surface tension, that is the thickness of the interface. Apparently the model works. So these are real experimental data obtained quite recently by students working in Bordeaux. So in the case where the green tagged polymer is inside the droplets, the size depends until you reach the optimal coating of the droplets, and remain constant, and the same is true, but for different values of the optimal concentration for the untagged polymer. And that size here that is constant in both cases presumably not universal. It is related to the way we have been prepared before the system. So you are just shaking the sample. So you are preparing by mechanical excitation a given dispersed state, initial state, and if you are shaking very violently, you start from smaller, initially smaller droplets, and then by the greedy model associated to the Pickering emulsion stabilization ideas, those small droplets grow until there is enough surfactant material, so enough lamellar phase to coat their interface. So that size, this has not been experimentally verified yet, is presumably related to the initial size defined by the shaking, the initial shaking of the system. So from the very simple equations, we can predict extract the thickness associated to the model, and here we still have a problem. This shouldn't be within the resolution limit of optical microscopy, but still in the very first picture it seemed that we can see the thickness. So there is also work in progress in terms of measuring the thickness of the interface, trying to relate that to the surface tension, which is much more easily measured experimentally, of course. And to conclude, I can say that the polymer doped lamellar phase in the bond regime stabilize water-in-water emulsion in the segregative limit have been described from the very beginning, because those polymer doped lamellar phase are in equilibrium with the water polymer A, polymer B system in their liquid-liquid phase separation regime, and because since they can, let's say, adjust their scale by having superimposed together a few or many layers, they can match the interfacial thickness psi. So that's all. I should acknowledge the many people having worked with on this project, and well, thank you for your attention.
Questions?
So, hi, here. Yeah, so I got a little confused because you started with just a system of 2 polymers and water.
Yes.
And then if you wouldn't add surfactant, then they would just phase separate and you would get...
Yes, this is the standard and the PT with emulsion in general, so they phase separate.
So they separate.
Very quickly in the case of oil and water, but...
Then you added the surfactant and then you could stabilize the microemulsions, but then you would form this...
Okay, this is... yes, in principle you are right. In practice, this works only in the case of oil and water emulsion, where the surfactant molecule itself is a small object. The size of a surfactant molecule is typically 1 nanometer or perhaps, and the surface tension between oil and water is, let's say, large. So a small object is able to stabilize a thin interface.
Right.
That works, yes.
Okay, but now but in your system, when you added the surfactant so that it starts to form the layers on the lamellar part of the emulsion, right? This is what I understood.
Yes. So the
okay, so
this is a multi-scale problem. So the surfactant itself makes bilayers that are still remaining at the molecular scale. Okay, so about 3 nanometers in thickness.
Okay, but then what separates the bilayers? So there is water between the bilayers?
Yes.
Okay, so this part wasn't... So it's completely separate. So you have the lamellar phase and the water and then another lamellar, and then it goes to another phase? I mean, it would be very helpful if you made like a drawing or something of the structure of the drop with what are the layers and how the surfactants are...
Yeah, so perhaps they have no real drawing, but perhaps that electron microscopy picture is the most suggestive things that I can propose here. So, so this is the inner part of the droplet, a macroscopic droplet. And this is the outer part, the continuous matrix. So this is, let's say, polymer A rich phase, liquid, ordinary liquid. So this is polymer, I've said A, so polymer B rich phase. And in between, we hypothesize, and we're pretty sure that it is true because we also X-rays, information, and so on, that we have a skin, a thin skin, which is a dilute lamellar phase. So the surfactant molecules are making bilayers, very thin bilayers here. And in between, you have the polymer doped solvent. So you have polymer A-rich liquid, you have polymer B-rich liquid, and in between, you have a lamellar phase swollen by a solution that contains polymer A or polymer B, depending on the way we are preparing the system.
So it didn't completely phase separate. It doesn't have just pure water between the surfactant layers. So there is some polymers also there.
Some polymer in between, yes. Yeah. So the polymer doped lamellar phase is a phase in the thermodynamic point of view. Finite size here, but this is homogeneous.
Okay.
So
So this part wasn't very clear to me.
I'm sorry for that.
Okay, thank you.
Thanks, Frederic, for this very nice talk. It's amazing that you could find a kind of free energy limit for this complex system. What would be the behavior of changing the temperature in your model. Is it possible to include this also or not?
Yeah, well, it's yeah, presumably that's possible. But since the equal temperature problem is so tricky at the problem I want to tackle it, so means, let's say, consistently merging Milnor-Roux IDs with Flory-Huggins IDs, that I wouldn't dare to do that, let's say, immediately. Next year, perhaps. But of course, those polymer that phase separate, they are quite sensitive to temperature. So if you increase the temperature, typically they are becoming generically less soluble. So the chi parameter increases with increasing the temperature. The chi parameter in the polymer model. In the case of fluctuating bilayers, there is also a chi parameter, of course. This one is presumably much less dependent on temperature.
Question back here. Hi. So I'm fascinated that this is an equilibrium problem because I'm reminded of the structure of what was called a lamellar onion state, which was stabilized by oscillatory shear. You had to really strongly disturb a swollen lamellar phase to get these concentric sphere structures. And so I'm just curious if in theory or experiment you have made any contact with the rheology or looked at the history dependence of these kinds of structures.
Yeah, so the case of onions that are obtained under shear is quite different. Here in this case, this is physical chemistry at the lab level. So we are mixing things this way. Of course, we should do that in cells where we can control rheology. But this is not yet done. I don't think this is really relevant at the present stage because the lamellar phase we are using, so this is basically a piece of soap, well, with some water added up to the bond limit. So the onion structure, well, what I've shown is reminiscent of an onion structure, but it is, well, the description is basically a quasi-unidimensional description. So all the ideas I've presented here should work with a completely phase-separated polymer A phase with floating above it a polymer B phase, and in between an oriented lamellar phase. Well, this is, of course, quite ideal view of the system.
More questions?
I can ask another question.
Yeah.
What prevents droplet fusion? I didn't catch what exactly is the analogy with Pickering emulsions. Why don't they coalesce upon contact?
Well, in fact, I don't really know why a stabilizing agent, whatever its origin, is preventing or at least delaying the coalescence process. So even in standard oil-in-water emulsion, the interface is coated by surfactant molecules, and this is said to prevent coalescence. In the case of Pickering emulsion, so the surfactant molecules are replaced by solid particles. So perhaps mechanically deforming the interface is more difficult, but still this is a non-equilibrium system. The ultimate fate should be a phase-separated system. So here we have a third kind of stabilizing agent, which is the dilute lamellar phase. So why is it able to prevent the coalescence phenomenon? I don't really know.
Very nice talk. I had a very similar question because I remember the Edinburgh group, so Wilson, Poon, and Paul Clegg, they were working with Pickering emulsions using colloids to stabilize these droplets. So I was wondering, yeah, exactly the same thing. why don't you get coalescence as they do of these different droplets?
Why, excuse me?
You do not seem to get coalescence of your droplets. Whereas in if you have colloids, they do coalesce every now and then.
Well, I said that also the lamellar phase is able to stabilize. This is not a long-term stability, of course. So they still but the same is true with Pickering emulsion. I think they nevertheless at some point, very slowly perhaps, they coalesce, and ultimately the Pickering particles are phase separated from the phase separated emulsion.
Yeah. And sorry, one last question. Could you control monodispersity of your droplets, so the size?
If we should, of course, but we are not yet controlling that. So in fact, the model described for based on Pickering-like emulsion was assuming, I've not said that explicitly, so sorry for that, assume that all the droplets are the same size. So this relates to the fractionation preparation procedure. So we are just shaking things which is not very controlled, but using mixer with controlled flow, we should be able to start from rather monodispersed droplets and adding then the lamellar phase in its bond regime. Then that should be better. Well, so the curves I've shown here are somehow misleading. Where are they? Yes, these one. So you see there is quite, experimental noise, of course, and in fact, in the true measurement, of course, the droplets are polydispersed. So the value here is a kind of average on a few hundred droplets.
Okay. Can I ask one last quick question? Sorry, it just came to my mind that a few years ago, Francesco Shortin and Dan Frankel independently suggested that sometimes you might have some sort of interrupted spinodal decomposition, so your system actually does not fully undergo a spinodal decomposition, but it stays, it just stuck in this sort of micelles-like behavior. So could your system remind an interrupted spinodal decomposition, so eventually your system will not fully phase separate?
Well, so if you want to describe things at, let's say, some kind of theoretical level in terms of spinodal decomposition, you have to characterize that in terms, let's say, of derivative of the free energy. So, well, I'm already in trouble with the three-component free energy incorporating lamellar phase and polymer. So, this is extremely interesting in principle, but I give you the way if you feel bold enough to do that. But of course, that's something which should be done.
Thank you.
Okay, let's thank Frederic again. So it's already 11, and we are supposed to be back to the